Section 10.4, Adding and Subtracting Radical Expressions. This is a nice, easy section. You'll notice that this section goes on only for 2.5 pages, and of that, 2 full pages are examples. There's actually nothing new in this section. Everything that we need to know to be able to work these problems, we already have. Adding and subtracting radical expressions. We're going to be looking at problems like this. 5 square roots of 6 plus 8 square roots of 6, and we're going to be asked to simplify. Well, these are what are called like radical terms. That is, the radical parts match exactly, not only in their radicand, but also in their index. Radicands are both 6, the indices are both 2, they're both square roots. And so this is the same as simplifying this expression. Over here, we combine like terms. In our radical expression, we combine like radical terms. 5 square roots of 6 plus 8 square roots of 6 totals 13 square roots of 6. You may notice that when I read these expressions, I don't say 13 times the square root of 6. I say 13 square roots of 6. And that's an older way of saying it, but I think it really makes sense in the light of these problems. 5 square roots of 6 plus 8 square roots of 6. It just sounds like it should be a total of 13 square roots of 6. 13 of them. 13 what? 13 square roots of 6. Now be very careful. If I have something like 2 square roots of 3 plus 4 square roots of 5, and I say simplify, well, that's it. Those are unlike radical terms. This would be just like asking you to simplify 2x plus 4y. 2x plus 4y is already simplified. So is this expression. And be very careful. 2 cube roots of 7 plus 4 square roots of 7, that's the same deal. These are unlike radical terms. One's a cube root, one's a square root. And so these don't match in their radical portion. This is already simplified. Let's work some homework problems. Let's start with number 6. Number 6 is just a little warm-up. This is actually an order of operations problem. We just have to crank this out. The square root of 25 is 5. Square root of 81 is 9. A difference of -4. That's all there is to that one. Let's take a look at number 8. Four square roots of 32 minus 2 square roots of 8. Now I see those are unlike radical terms, but is this expression simplified? Well, 32 contains a 16, doesn't it? And we're not allowed to have any perfect square factor under a square root. We've got our 4 floating out front. 32 contains a 16. It's 16 times 2. So my 4 is floating out front. Square root of 16 is 4. And the 2 is stuck inside. So this ends up giving me 16 square roots of 2 for this first term. Minus 8 contains a 4. 8 contains a factor of 4 that needs to be dealt with. We have our 2 that floats out front. And 8 is 4 times 2. Our 2 that floats out front. And then here, square root of 4 is 2. And this other 2 is stuck inside. So this gives me 4 square roots of 2. Let me use just a little color here to make sure, because we have a lot of duplication of numbers in this problem. Let me make sure that we see exactly where everything is coming from. 32 is 16 times 2. And that square root of 16 gave us this 4. 8 was the square root of 4. And the square root of that 4 is this 2. So we've simplified each term, and then we look here at the end and we go, oh, those are like radical terms. We can subtract these. 16 square roots of 2 minus 4 square roots of 2, a difference of 12 square roots of 2. And that is now simplified. Let's go with number 18. This is going to be a very similar problem to the one that we just worked. Initially, we glance and we say, well, those are unlike radical terms, but there's a lot more to consider when it comes to simplifying radicals. We have to determine, do any of these radicands contain any factors which are perfect squares? 54 contains a 9. 54 is 9 times 6. Square root of 9 is 3. The 6 is stuck inside. And then my floating 5 times that 3 is 15. 15 square roots of 6. My first term simplifies down to. My second term now, minus 2 times the square root of 24 contains a factor of 4. It's 4 times 6. You can already see we are going to have at least a pair of like radical terms. We'll have to wait and see what that third guy does. We have our floating 2. Right here, the square root of 4 is 2. And square root of 6. The 6 is stuck inside. 2 times 2 is 4. 4 square roots of 6. And now our last term, we might have to ponder on this for a minute, but we will eventually discover that 96 contains a 16. 96 is 16 times 6. And here again, this is why I say you've got to have these powers memorized. You've got to know your multiplication tables up one side and down the other. You've got to know your rules of divisibility so that we can get results like this fairly quickly. We've got our floating 2. Square root of 16 is 4. And the 6 is stuck inside. This gives me 8 square roots of 6. Well, these are all like radical terms. This is just like working out a problem 15x minus 4x minus 8x. Except instead of x, these are square roots of 6. 15 square roots of 6 minus 4 square roots of 6 minus 8 square roots of 6. 15 minus 4 is 11. Minus 8 is 3. 3 square roots of 6. Or honestly, the way I would do that, I'd say 15 and what? Minus 12? 15 minus 12 gives me that same 3 square roots of 6. That was number 18. Let's jump back up now to number 12. So the first thing I need to do is look and see if any of these radicands contain any factors which are perfect fourth powers. Those are a little tougher to spot because they are bigger numbers. 405. If I get completely stuck, I would probably start to prime factor. And I know it's a multiple of 5. I know it's 5 times something. 5 times what? 5 times 81. Oh, well, right there's a perfect fourth power. 81 is 3 to the fourth. So I don't need to finish my prime factoring. I've already discovered, quite happily, the perfect fourth power that is contained in 405. 405 is 81 times 5. This second term is already simplified. Let's continue working on the first term. Fourth root of 81 is 3. This gives me 3 fourth roots of 5 minus 2 fourth roots of 5. A difference of 1 fourth root of 5. Of course, we don't write the 1. This is simply the fourth root of 5. Just like 3x minus 2x would be simply x. Number 20. Let's simplify each term and see what happens from there. So, does 18k contain any factor which is a perfect square? Well, 18 contains a 9. It's 9 times 2. And a single k does not contain a perfect square. Square root of 9 is 3. So this is 3 square roots of 2k. And minus... does 72 contain any factor which is a perfect square? I showed you a 72 the other day. It's best to get the biggest perfect square factor out right off the bat. We know 72 contains a 9, but remember what we saw the other day. 72 contains also a 4, meaning 72 contains a factor of 36. It's 36 times 2, and times that k. Square root of 36 is 6. So this term is minus 6 square roots of 2k. Those are like terms. They're like radical terms, so we can subtract. 3 of them minus 6 of them is negative 3 of them. Negative 3 square roots of 2k. All right, let's have a go at number 24. Now this section is kind of the calm before the storm. This is a nice, straightforward, short section compared to 10.5. 10.5 we're going to have some work to do, so just be prepared for that. Enjoy this section while it lasts. 10.5 we're going to have to put in a little more effort. So, simplify each term. Does 81 contain any perfect cubed? Well, 81 is 3 to the 4th, so I know it contains 3 to the 3rd. I know it contains a 27. Our 15 floats out front. 81 is 27 times 3. That's 3 cubed times another 3. 3 to the 4th, that's 81, right? The cube root of 27 is 3. And this other 3 is stuck inside. We multiply to get 45 cube roots of 3 as we simplify that first term. And plus, what do we have here? Our 4 floats. Does 24 contain a perfect cube factor? It sure does. It contains a factor of 8. It is 8 times 3. Cube root of 8 is 2. 3 stuck inside. And so this finally gives me 8 cube roots of 3 for that last term. These are now like radical terms. And so we finish it off by combining. 45 of them plus 8 of them gives me 53 of them. 53 cube roots of 3. Make sure your index is tucked nicely in that little check mark. Now I want you to be very careful. Let me just make one up for us. Let's think about this. 2 square roots of 50 plus 3 square roots of 12. Simplify. First we'll simplify each term. 50 contains a 25. It's 25 times 2. Square root of 25 is 5. So this first term is 10 square roots of 2. My second term, that 12 contains a 4. 4 times 3. Square root of 4 is 2. And so we have 6 square roots of 3. These are unlike radical terms. So there's nothing else I can do. This would be my final answer. And in multiple choice, all the things I can do in multiple choice. I guarantee you one of my distractors here is going to be 16 square roots of 5, because someone is going to add what's inside those square roots, which you can't do. Cannot do that. And I've got a few other good wrong answers for this one. It's important to know how to simplify. It's important to know when to stop. It's important to know when to stop when you have nothing else that can be done. When there's nothing else that can be done, some people like to make up their own rules and say, oh, I'll keep going. Well, you don't have that luxury of deciding what the rules are. So here we have to stop when we see those are unlike radical terms, but we did have to do what we did. We're not allowed to have perfect squares under a square root, so we did have to simplify each term. It's just in this particular case, we can't go any further because we have no like radical terms to add together. All right, let's look at number 30. Indices tucked nicely in the check mark. Powers clearly outside of that little check mark. I don't want this to look like q to the 23rd or a plain q with a 23rd root of something. Make it very plain and clear exactly what this says. All right. Simplify each term. We have two terms here. My first term is simplified. In my radicand, I have a 5 and a q. None of that contains any factor which is a perfect cube. But in my second term, I've got some things going on. In my second term, in my radicand, I have 40q to the 4th. Does that radicand contain any factor which is a perfect cube? Well, 40 contains an 8. It's 8 times 5. q to the fourth contains a q cubed, leaving one q behind. So this is going to give us our floating 2q, and then right here, the cube root of 8 is 2. Cube root of q cubed is q, and my 5q is stuck inside. You see, the only thing I did in that step, was deal with this cube root of 8q cubed, which gave me this 2q. That's the only thing that happened in that step. All right, our first term is just tagging along. He's waiting to see what's going to happen. Two q times 2q is 4q squared. And these are like terms. These are like terms in q squared cube roots of 5q. In other words, the only difference here is in these numeric coefficients. We have 6 of them minus 4 of them, a difference of 2. Let's go ahead and make that pink, just to keep track of what we're doing. A difference of 2 of them. 2 what? 2 q squared cube roots of 5q. And notice how we take this just a little piece at a time. These are good problems, once again, to bear in mind. You bite off more than you can chew, you're going to make some silly mistake that's going to cost you points. And it's better to put in the extra step and make sure that you've got it. Let's go with number 40. I can already tell you that at the end of this problem, I'm not going to have like radical terms. Do you see that? One of these is a square root, the other is a cube root. But I have to check and see if I can simplify the individual terms. Does this first radicand contain any factor which is a perfect square? Yes, it does. 125 contains a 25. It's 25 times 5. A to the 5th, what's the biggest perfect square in a to the 5th? Perfect squares have even powers. A to the 5th contains an a to the 4th, leaving one of those a's behind. B to the 5th likewise contains b to the 4th, leaving a b behind. Let's go ahead and finish up this term. Square root of 25 is 5. Square root of a to the 4th is a squared. Square root of b to the 4th is b squared. Everybody else is stuck inside. And plus, does this radicand contain any factor which is a perfect cube? Well, 125 itself is a perfect cube. A to the 4th contains an a cubed, leaving an a behind. B to the 4th contains a b cubed, leaving one other factor of b. Cube root of 125 is 5. Cube root of a cubed is a. Cube root of b cubed is b. And everybody else stuck inside. Remember, we can always, when we have our variables to powers, we can use that idea of long division We could have done it in the previous problem with our q's. But here I could have said, well, I'll deal with the 125, which will give me 5 square roots of 5. But then what about my a's and my b's? Well, right here. 5 divided by 2. 5 divided by 2 is 2, remainder 1. And again, 5 divided by 2, 2 remainder 1. We could have done the same thing here. Square root of 125 is 5. For my a's, 4 divided by 3 is 1, remainder 1. And for my b's, 4 divided by 3, again, 1, remainder 1. So don't forget, you do have that technique at your disposal. I will typically show the problem done this way, but I will often remind you of that long division with remainder technique that we do have, that we can use. Alright, I took care of perfect squares under a square root, perfect cubes under a cube root. Is there anything else I can do to simplify this further? No, these are very much unlike terms. And so, that's simplified. Alright, now I've got one for you to try. Let's back up and look at number 36. The number 243 should look familiar to you. That should jump out at you and say, hey, look at me. That's all I'm going to say about this one. I'm going to let you pause the video here and come back when you're done and we'll compare answers. That 243 should look familiar. That's 3 to the 5th power, isn't it? And we're looking to see if this radicand contains any factors which are perfect 4th powers. Well, 3 to the 5th contains 3 to the 4th. So yes, it does. Our floating 5. 3 to the 4th is 81. 243 contains an 81. It's 81 times 3. There's your 3 to the 4th, and there's your other 3 to make 3 to the 5th. X cubed, that power is not big enough to contain any 4th powers. There's nothing I can do with this second term. Back to my first term, we have our floating 5. 4th root of 81 is 3. The rest are stuck inside. Five times 3 is 15, so we have 15 4th roots of 3x cubed plus 2 4th roots of 3x cubed, a total of 17. 17 of them. 17 what? 17 4th roots of 3x cubed. How'd you do? Alright, you're going to like these next ones. Let's look at number 46. What the heck? Throw in some fractions, right? Number 46. 4 cube roots of 3 over 3 plus 2 cube roots of 3 over 9. Now, first of all, be aware, and we'll make this much clearer in the next section. This 3 is inside a radical. This 3 is outside. They cannot see each other. Don't try to cancel anything. This 3 and this 9 cannot see each other. The 2 and the 9 can see each other. They're both on the outside. In fact, this is the same as 4/3 square roots of 3 plus 2/9 square roots of 3. In order to add fractions, I have to have a common denominator. Least common denominator for 3 and 9 is 9, so I need a factor of 3 over here. Now again, even if I were to write this, let me write this over here. Even if I were to write times 3 times 3, that blue 3, what can he get together with? He is outside the radical. So he can get together with the 4, but this blue 3 and this radicand of 3 cannot see each other. So here in the top, we now have 12 square roots of 3. 4 times the blue 3 gave me that 12. This is over 9. Plus 2 square roots of 3 over 9. See that these are like terms. See that they match in their radical and their denominator. So what do I really have here? I have 12 of them plus 2 of them. Twelve of them plus 2 of them is 14 of them. 14 what? 14 square roots of 3 ninths. And there would be nothing wrong with writing my answer as 14 ninths square roots of 3. I could work the problem in this form, still get the same thing. These two are perfectly equivalent to each other. All right, let's look at number 48. Number 48. The instructions, her instructions read, perform the indicated operations. My instructions will probably just say, simplify. Simplify. We know one of the rules of simplification of radicals is we are not permitted to have a fraction in the radicand. That's an easy fix with our quotient rule. This is square root of 12 over square root of 16. My second term, square root of 48 over square root of 64. Let's keep going. Well, these two denominators, those are nice square roots of perfect squares. Let me go ahead and clean those up. Square root of 16 is 4. Square root of 64 is 8. Those are out of the way. What about that 12? It's not a perfect square, but does it contain any factor, which is a perfect square? 12 contains a 4. It is 4 times 3. And so square root of 4 is 2. This is 2 square roots of 3 over 4. Now what about this 48? Does 48 contain any factor, which is a perfect square? Okay, now watch carefully on this one. You don't have to write this bit down because I'm going to change it. 48 does contain a 4. It's 4 times 12. But what? That 12 contains another 4. This is one of those situations where it's best to get that biggest perfect square out the first time. 48 contains a 4 and another 4. That's a 16. 48 is actually 16 times 3. And the square root of 16 is 4. So 4 square roots of 3, and that's over 8. We've simplified both terms. Can we keep going? Yes, we can, because these are like radical terms. These are like radical terms. And so to add these up, I just need common denominators for my coefficients. My coefficient here is 2/4. My coefficient here is 4/8. Instead of, now look and think, instead of changing everything to eighths, why not reduce these? 2/4 is 1/2, isn't it? 4/8 is 1/2. Remember what this really means. This is a 1/2 square root of 3 plus another 1/2 square root of 3. What is that total? 1 whole square root of 3. And if you see it that way, you're ready to write down your answer. Or if you want to do it this way, say, well, I now have a common denominator. Let me add the numerators. Square root of 3 plus square root of 3 is 2 square roots of 3, right? X plus x is 2x. This is 1 square root of 3 plus 1 more square root of 3 is 2 square roots of 3 over that common denominator. And then what? The 2's cancel. Either way, you end up with simply square root of 3. Nothing new in this section. Just a new type of problem. Combining like radical terms. Enjoy this section and be prepared next time to put in some work on section 10.5.